All right, I believe I'm recording. So this last part, I will email out these PowerPoints to you, but it's going to be a PowerPoint lecture. I don't want to write else on the board. So we're going to talk about Le Chatelier's principle. Again, last part of chapter 15. Le Chatelier's principle. If a system at equilibrium is disturbed by a change in temperature, a change in pressure, volume, we'll talk about that, or a change in the concentration of one or more components, the system will shift its equilibrium position in such a way as to counteract the effects of the disturbance, go back to equilibrium. So basically, what it's saying is you have a chemical equation of equilibrium. You alter it in some way or form, and then it's going to go back to equilibrium by shifting, is what Le Chatelier's principle says. Again, we're going to go into more detail about this, but basically three ways. Number one, adding or removing a reactant or a product, changing the volume and thus the pressure, and changing the temperature. So first, we're going to go change the concentration. All right. So say we have this chemical equation right here, the Haber process. We have N2 plus 3H2 goes to 2NH3, okay? Now, this equation is at equilibrium, all right? Now, we're going to add H2, okay? When we add H2 on this side, right, that's a reactant. What happens if you write out Q? The denominator becomes larger. Q is thus less than K. What did we say happens when it happened earlier? It shifts to the right to reestablish equilibrium. That's exactly what happens, okay? Um, Therefore, H2 and N2 will decrease and NH3 will increase until Q equals K. Let me go over that one more time. We have N2, 3H2 plus 2NH3. It's at equilibrium. We add H2. What happens to Q if you write it out? The denominator becomes larger, right? Q becomes smaller. Q is less than K. Our reaction shifts to the right to reestablish equilibrium. As it shifts to the right, we're going to lose N2 and H2, and we're going to get 2 and H3. And that's shown in the next slide. That's shown here. Again, here's our reaction. Here we're at equilibrium. H2, NH3, N2 are all at constant concentrations. We add H2 shown here. What's going to happen again? I told you the reaction will shift to the right to reestablish equilibrium. So the concentration of H2 is going to decrease shown there until it reaches equilibrium. N2 also, since it's on the reactant side, the concentration is going to decrease until it reaches equilibrium. What happens on the product side? The NH3 increases in concentration. Again, now Q will equal K, and the world is happy, and the equation is once again at equilibrium. Now, we could do more. There's other ways we could affect this, but I hope the basic principle is understandable. Let's look at some more examples. If we had N2, that's similar to adding H2, right? Q would be larger. Our reaction, Q is less than K, our reaction would shift to the right. Now, another way to look at this without having to think about Q is think about this is a balance. Your reactants are on one side, your products on the other side. Think about the fulcrum, the balance point is right here, right? So at equilibrium, both sides are balanced, right? At equilibrium, see, like with weight, both sides are balanced, all right? Now you add N2, what happens to your scale? This side goes down. To get it back to equilibrium, what do you have to do? You have to transfer stuff from the reactant side to the product side. Okay, that's another way to think about it if you don't want to think about Q. If we add NH3, what's going to happen? Again, here's your fulcrum point for your scale. You add NH3. This side's going to go down. To establish equilibrium, what do you have to do? You have to transfer from products to reactants. Vice versa, but we can also remove one of the chemical species. So if we remove H2, what happens to our reaction? Again, think of this as a scale, right? Here's your fulcrum point. You remove H2, what's going to happen? This side is going to come down, right? The product side will be heavier, quote unquote. What's going to happen? Your reaction is going to shift to the left, to reactants. Same thing with N2. If you remove N2, what's going to happen to your scale? Again, this side, reactant side would go up, this side would go down. To get back to equilibrium, what do you need to do? You need to go from, products to reactants. Sorry about that. From products to reactants. If you remove NH3, what's going to happen? Again, your fulcrum point, this side's going to go down. To get back to equilibrium, you got to shift to the right. So now, you need to either memorize this or think of Q or however you need to do it to get into your head, okay? But you have to know Le Chatelier's principle, right? Now let's look at a change in volume and thus pressure, basically, okay? If we change the volume of gaseous reaction to equilibrium, this will affect the partial pressures of the gases, and Le Chatelier's principle predicts it will cause a shift in equilibrium. Okay, there are 4 cases. If we decrease volume, that increases pressure. It favors the direction that has fewer moles of gas. So the side of the reaction, you decrease the volume, increase the pressure. The side of the reaction that has fewer moles of gas will be favored. Okay? Again, we'll look at an example here in a moment. Number 2, right here. If you increase volume, pressure decreases. Okay? It decreases pressure. That favors the direction that has more moles of gas. So the side that has more moles of gas, when you increase the volume, the reaction will shift that way. Number 3, in a reaction with the same number of moles of gas in the products and reactants, changing the pressure has no effect on the equilibrium. So if they're the same on both sides, then it does not change the equilibrium. Number 4, if we increase the total pressure by the addition of a gas that is not involved in the reaction, there will be no change in equilibrium. So say you add He to a gas. He is inert. It's not going to change the equilibrium. Now let's look at an example. So here we have a generic example. Here we have 2 moles of chemical A, if you want to so to speak, right? 2 of A and 1 of B, right? So here we're at equilibrium, right? We're initial volume. We're at equilibrium here in the middle. I decrease the volume and thus increase the pressure. What did I say that does? It increases this, favors the side with more moles of gas. If you count them up here in the middle, you're going to have the same number of red and the same number of these, whatever color that is, I don't know, gold. As we decrease the volume, increase the pressure, the reaction shifts to the right. Okay, don't ask me why they put that on the left side. It seems kind of dumb to me. But anyway, the reaction shifts to the right. We get more B as you decrease the volume, increase the pressure. Vice versa. Again, we're at equilibrium. You have 2A, and you have 1B. Okay, again, 50-50 here at equilibrium. Now we increase the volume and decrease the pressure. What did I say according to Le Chatelier's principle? You favor the side with more moles of gas. So what's going to happen? You're going to get more of the red. You're going to get more A, right? The gold, whatever, B, is going to decrease, right? I hope I'm making this clear. Again, remember, if we have this reaction and I add He, what's going to happen? Nothing. He is an inert gas. It's not going to change the equilibrium one way or another. If we had the same on both sides, again, remember, if you had, say, 1A and 1B, and you increase the pressure, decrease the pressure, it doesn't change the equilibrium, right? It stays the same if the same number of moles of gas are on both sides. Now we have one more thing to consider, and that's temperature, right? Now, side note, right? You might remember that the equilibrium constant, K, Kc or Kp, is temperature dependent, will vary with the temperature. But that's not what we're talking about here. Although K will change with the temperature, okay? Fine. Now, let's look at Le Chatelier's principle. How will change in temperature alter a system at equilibrium according to Le Chatelier's principle? It depends on whether the reaction is endothermic or exothermic, okay? Now, what you're going to do is you're going to treat heat as a reactant or product, is what you do. And then you can use the scale example. An endothermic reaction, delta H is greater than 0, you're going to treat heat as a product, okay? Or, sorry, I'm messing up. It's right there. Endothermic, you treat heat as a reactant. It's on the reactant side. Endothermic, delta H greater than 0, heat is a reactant. When it's exothermic, delta H less than 0, you treat heat as a product. Now, just like before, when we have our reaction, okay, whether it's exothermic or exothermic, let's say you have an exothermic reaction. Again, think of this, your reactants, products, think of this as a fulcrum point, right? A balance. Now, at equilibrium, both of these will be the same. When you add heat, it's like adding products. It would shift to the left. If you take heat away, make it cool, you're taking heat away, it would shift to the products. I said that wrong the first time. I said we shift to reactants. Here, there's a better example coming up. Sorry, blah, 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 blah. Here, let's look at this. This is better. All right. So here we have this reaction. My mouse is messing up. Here we have this reaction. Delta H is greater than 0. That means that it's endothermic. So put heat over here on the reactant side right there. Now this particular reaction, when The equilibrium lies on the reactant side, it's pink. When it's on the product side, depending upon the temperature, it's blue, okay? It's blue, right? So now here we have at equilibrium, we have significant amounts of both pink and blue, although it looks pretty blue to me, but anyway. Now, we add heat. If we add heat, what's going to happen? You add heat here on the reactant side. What's going to happen? Your scale is going to go down, and you're going to shift to the product side. Okay? You're going to shift to the product side. All right? Again, your scale here, you add heat, you're adding reactants. This side of the scale goes down. What do you got to do to go back to equilibrium? You got to go from reactants to products. Vice versa. You're at equilibrium. Now, we cool it down. We stick it in ice water, okay? We cool it down. You're taking heat away. Again, remember, this is your fulcrum here, your balance. You're taking heat away. What's going to happen? This side's going to go up, this side's going to go down. If you're looking at like a scale, right? To go back to equilibrium, what do you need to do? You need to transfer products to reactants to go back to equilibrium. Okay? Again, I hope I explained all of that properly. Or understandably, I should say. Also, again, Le Chatelier's principle, note, addition of a catalyst to a chemical reaction will not change the equilibrium. Remember, a catalyst speeds up a reaction by decreasing the activation energy. It will not change the equilibrium point. It just speeds up a reaction. That's all it does. And that's all I have. And that's the end of chapter 15.